these things we've got to use composition function that we talked about last week. So we're going to start with 1 and 2. And what we're doing here, like I said, we're proving these things are inverse functions. And the way we do that is if we look at the composition, only thing we should get out is x if they're inverses. And spoiler alert, these two sets of functions, both 1 and 2, are inverse functions. So we should get x out either way we plug them in. I think this one might be the tougher one because u fractions. But we're going to work through it because, like I said, I think the algebra there is the tough part. So let's compose. So we're going to do both. We do both of them like it says. So we want f of g of x. So we want to replace in the equation that is g of x in here. So this means that we want to go f of x squared plus 4. So we want to take the x value in f and make it x squared plus 4. So this x is going to turn into x squared plus 4. So we get x squared plus 4 minus 4. And what we're looking for here is we want to get just x out of this thing. So we've got to simplify it. That's the tough part of these. Once we get everything written in here, we need to work with the simplification. So first thing, we don't need the parentheses. So this is really x squared plus 4 minus 4. So these things are going to cancel out underneath the square root. Which now we get the square root of x squared, the square root of x squared, which is x. So when we composed them this direction, we got x, which proves that they're inverses. Now we can do this both directions. Usually don't need to prove them both ways. If you do it once, it's going to work for the other one. But let's practice with both. So we're going to do g of f of x. So that means we're going to take the g function, and we're going to plug in this square root of x minus 4 wherever we see x in it. So in here. So we're going to get the square root x minus 4 squared plus 4. And again, the algebra on this is probably the tougher part, but square and square root are inverses. And that's the other thing you look at. For all this stuff to cancel out and us just to get x, you're going to have inverse functions all over the place that are going to undo each other. So that's going to cancel, and it just leaves us x minus 4 plus 4, which gives us x again, which proves that these are inverse functions. Now, as the functions become more complex, the algebra becomes a little bit more difficult, okay? But it's all about this result. If I compose two functions and the result is just the variable, those two functions are inverse functions. They will undo each other. So let's try the one that's a little bit tougher because we've got rational functions. We're going to do the same thing. We're going to find f of g of x and g of f of x. So let's start with f of g of x. And what I told you when we worked with these, or if you watched my video from Monday when we talked about them, usually I say you only need one of these. Pick the one that might be a little bit easier. Neither one of these is going to be easier. X is in the top and the bottom of these fractions on both sides. It's going to be messy no matter what, but they are inverse functions, I promise. So that means we're going to take the f function and we're going to plug in 2x plus 3 and x minus 1 everywhere we see x. So in f, these two x's are now going to be replaced with that. So that means that this is equal to, it's going to be a big fraction, 2x plus 3 over x minus 1 plus 3, and 2x plus 3 x minus 1 minus 2. And so for all these compositions, we still need to simplify them because the result that comes out being simplified is what we're hunting for. So that means we need to add these things. So let's remember how to add fractions here. I have 2x plus 3 over x minus 1, and I want to add 3 to it. That 3 is also a fraction. It's over 1. And you have to remember to add fractions, we need common denominators. So that means the second fraction needs x minus 1 on both the top and the bottom. So it's going to simplify it to x minus 1, just one of them on the bottom. I don't need to put anything over here because this is just times 1. 1's not going to change anything. And then I just need to simplify the top. So that's 2x plus 3 plus 3x minus 3. I distributed and then I added them. So the top of this thing turns into 5x over x minus 1 because the 3's cancel. You can start seeing the inverse operation springing up here and things are going to cancel out. So the top of this is 5x over x minus 1. Now we need to do the same thing. We need to do common denominators and add for the denominator of this. So I'm going to erase this part. We're going to do the same operation off to the side. So we had 2x plus 3, x minus 1, and this time we want a minus 2. You got to be careful because of this minus over here, but we still need common denominators. So when we simplify, we just get x minus 1 on the bottom. The top is 2x plus 3, and this is going to be negative 2 times both of those things. So it's minus 2x plus 2. So this time, this is going to cancel. So we're just going to end up with 5 over x minus 1. Doesn't look a whole lot simpler. I mean, it does look somewhat simpler, but it doesn't look like we're getting much closer to just getting x out of this thing. But now we got to remember another one of our fraction rules. We are dividing two fractions. We can also write that by the multiplication of the inverse. Keep it, change it, flip it. So this is 5x over x minus 1, that's the numerator, times, flip the denominator over. And now that turns into 5x, x minus 1 over 5 times x minus 1. And now all that stuff, you see, it's all going to cancel out. The 5's cancel, the x minus 1's cancel, and we do end up with the x that we expected because these were inverse. Had to go a long way to get there. Fraction rules. Make sure you review them constantly, especially as you work from pre-calculus into calculus, okay? Because getting comfortable with the stuff that we did on the top and the bottom here, the numerator and the denominator, is going to be real important as you move on. Now we are going to do the second one. So we're going to do g of f of x. It's going to be very similar. And since we know these things are inverses, we should end up with x out of this. So we want g of x plus 3, x minus 2. So that's going to give us 2 x plus 3, x minus 2 plus 3, and x plus 3, x minus 2 minus 1. So now we've got to deal with combining the numerator and denominator stuff. So the first thing is we've got to multiply this 2 to everything. So we have, let's look at what we have here. We have 2 over 1, x plus 3, x minus 2, and then we want to add 3 to that thing. We multiply before we add. So the top gets multiplied by 2. Denominator doesn't change. And now we end up with our common denominators. So this is going to get x minus 2 So we end up with everything over x minus 2, and we get 2x plus 6 plus 3x, and that's going to be minus 6. So our 6's cancel. And what does our top turn into this time? This is 5x left on the top over x minus 2. So the numerator is 5x over x minus 2. We've got to repeat that process and do that subtraction of that rational stuff on the bottom. So we've got x plus 3 and x minus 2, and we're going to minus 1. No need to worry about multiplication, just common denominators again. X minus 2, x minus 2. So this is x minus 2, and this is going to be x plus 3 minus x plus 2. You've got to distribute that negative to both of them. X's are going to cancel, and the top is just 5 over x minus 2. And because we've done the first one, there's a reason I wrote these right here. Notice that these are very, very similar, right? Same thing is going to happen here, and that's what you should be kind of seeing as you compose these things. The numbers might change positions, but you're still going to be left with a whole bunch of inverse functions that are going to cancel. We're still going to do this keep it, change it, flip it. But we still have 5x and 5 on the top, like we did here. The denominator's changed, but it's still the same. We're going to end up with the same result. 5x over x minus 2. X minus 2 over 5. So this leaves us, because these combine now, hey, look, everything canceled out again. And there's that x that I expected to prove that they're inverses, okay? The concept that we're working with isn't the tough part of this. It's all the algebra that goes in it that we've learned before, okay? So especially dealing with rational functions. If you look through some of the notes, make sure you remember your inverse operations as you do these things. You know, square and squared root, cubed and cubed root, multiplication, division, things like that. Those are the things that are going to happen as we cancel out. Now, if I asked you if two functions were inverses and you did this work and you didn't get x, what does that mean? It means that they are not inverses. Okay, both of these examples I did were inverses, so we knew where we were going because I wanted to focus in on the algebra. But remember what the result proves. Here we're verifying that these are inverses, and the fact that we get the x out of the composition verifies that these things are inverses. And what I'd always say too, if you try f of g of x, and you know they're inverses and you get stuck and something doesn't work, try the other one. Because just flipping it around, it may become a little bit easier with the way the operations cancel to lead you in that right direction, okay? So that's verifying inverse. Verifying an inverse composes the two functions and we get x out. That was Monday. Tuesday, we talked about domains. Now, there was a method to this. So the first thing we talked about is finding the domain and range of a function from an equation. And when you find, I'm sorry, not domain and range, but just domain. When you find domain, there's only two things you need to look out for: the square root and the rational. Because those are our two exceptions. If your function doesn't have a rational part to it, rational function, or a square root function in it, then its domain will always be negative infinity to positive infinity, or all real numbers. Meaning, if one of my functions was that, so this is x squared plus 3x, does that have a radical or a rational in it? So that guarantees that its domain is everything. every time. All polynomial functions, think back to last unit, every one of those polynomials that we dealt with, we're learning where they cross the x-axis. Every polynomial always has a domain of negative infinity to positive infinity. The only thing equation-wise that will ever mess you up if we have a rational function or a square root function. Now we want to talk about domains of compositions. So obviously we're going to work with some of the exceptions here, so the answer is not just always negative infinity to positive infinity. So when you go, before you start the whole composition process, find the domain of the two functions you're starting with. So both of these are rationals. What can't happen in a rational? What can't we divide by? We can't divide by 0. So the way we figure out what we have to skip in these domains is we have to take the denominator, figure out what makes it equal to 0. We're really finding where the vertical asymptote of this rational function is. So this one is at 0. Now the only thing that you'd kind of add to this to make the math make more sense, I know that this can't happen, right? That's the part that I want to skip because that's the one exclusion in the domain. So because the denominator here is x, I know that x can't take on the value of 0 because I can't divide by 0. That's the only spot, and if we look at this on a number line, that's the only spot that I have to leave open. Every other number is fine to divide by. So that means that the domain of this thing is negative infinity to that 0, but we don't include that 0. We jump over it and we start over here. We go 0 to positive infinity. It's everything except 0. It's like a hole punch. Rational functions are like hole punches. They punch holes inside our negative infinity to positive infinity domain, and we just have to figure out where that spot is that we need to skip. So that's the domain of the first one. Find the domain here. We actually do a little bit of algebra. So this means x can't be 2. So that means we're going to have to skip 2 this time, but it's still everything else. So the domain of this one is negative infinity to 2 and 2 to positive infinity. Those are the domains of the individual pieces that I'm going to compose. Because when we look at the composition and we find the domain of the composition, we need to keep this if it's the inside function. Because when we compose, we have to go through and do all this simplification stuff. What can happen is we could lose that restriction algebraically by simplifying it. Things could cancel out if they end up being, some of them being inverses, okay? Because we composed this and we got x here. But we'd still have to skip positive 2 because it's what makes the function that we inputted equal to 0. We just lose that domain restriction when we go through and compose them because we only get x out, and x doesn't have any restrictions on it. So let's go through and actually find one of the compositions. So let's do f of g of x. So f of g, that means f of g of x. So we're going to plug g into f. So we want f of x over x minus 2. So that's going to be negative 3 over x minus 2. So we get another fraction nested with a fraction. Now this one, there's nothing in the numerator and the denominator that we need to add to get it to one fraction. So this one we can just keep it, change it, flip it. So we're going to get negative 3 over 1 times x minus 2 over x. So the composition function is that. Now we're going to find the domain of this just like we did above. So when we find the domain of this thing, we have to skip what makes the denominator equal to 0, which since we just have x, that means the domain of this function right now, not listed up there, let's list it down here, tells me to skip 0, right? But what I have to include with this is I have to include any domain restrictions from g of x that might not be in this answer. So g of x told me to do what? G of x told me I had to skip 2. So when you go through and you look at this, we can use this number line idea. This was g of x. It told us skip 2. Then we did f of g of x, and we found that composition and found out we also had to skip 0. The overlap is what the answer should be, meaning that I need a number line that includes both of those skips. I need to skip, and I put them in the complete backwards order. That's not anywhere near where it should be. Sorry, guys. I need to skip 0 and 2 when I find the domain of the composition. Because what happened is through the algebra, I lost this restriction. But because I know what I started with, I know what I plugged into the function, and it has its own restriction, I still need to include it for this composition. So that means the real domain of this composition function, and this only has to happen because I know it's a composition. This is going to be -infinity to 0 with 0 to 2, and then 2 to positive infinity. Yeah, it's long, right? Everybody get that out of the work the other day? I saw you guys working on it. So it's weird. Whenever you do a composition, find the domains first, then find the compositions and find the domains of them and just see where they overlap. It won't always be that you have to include stuff from both of them. Sometimes when you go through and you find them, the domain of the composition will already include whatever restrictions are in the first one, so you don't have to change it. Let's try the other way and see what happens. So we want g of f of x. So that is g of -3 over x. So that's going to be -3 over x, -3 over x minus 2. I've got a minus in the bottom. That means I'm going to have to do common denominators and simplify. But remember, whenever I get done, I have to include the restriction here. So the restriction in this one told me that I needed to skip x equals 0. I'm going to figure out whatever restrictions this new function is going to have and see if that's already included in its domain. If it's not, then I'm going to make it include it. So let's see, we're going to get -3 over x. And when we do common denominators here, it's going to be -3 minus 2x over x. Then we're going to keep it, change it, flip it. So this x goes on top, and we get -3 minus 2x. X's cancel. My composed function is that. I guess the only thing we could do is factor out the -1, but I'm going to leave it in there because I think it's easier to find the domain with it in there. So this is g of f of x. Now I'm looking for its domain. So that means I need to know what makes -3 minus 2x equal to 0. because I have to exclude that thing. So that's negative 2x can't equal 3. So x cannot equal negative 3 over 2. Is the skip 0 included with what I have to exclude over here? No, because remember, if you looked at this, and I'm going to think about this on number lines, okay? That's why I drew that number line in there. This one had skip 0, so everything else was shaded yellow, because the shaded yellow part is what our domain is. Down here, I have the same picture, but it's telling me to skip negative 3.5. Everything else is okay. Those two hole punches don't line up, so that means when I write the domain of this composite function, and this only happens because I know it's a composite, that means I have to include both of these when I write my answer. Negative infinity, and you're going to hit negative first. And we're going to go negative 3/2 to 0. I'm going to write it below it because I ran out of room. We always list those negative to positive in order, okay? So I think the rational functions help kind of make this really come out. When you do when you do ones with the square root stuff, because it only includes, either there to positive infinity, most of the time the first function doesn't change much anything. So you got to be careful.